Hi, in this video, you will learn about Explainable AI or XAI frameworks toward interpretable system. So here we go. Well, let's start with a meme, and I really like it from KCD. The meme said, "Is this your machine learning system?" The guy said, "Yep. If you pour data into this big pie of linear algebra and then collect the answer on the other side." The other guy said, "What if the answers are wrong?" Just stir the pie until they start looking right. So in that sense, that a lot of machine learning have this sort of a skew view of how the data was actually processed, and that's what called the black box AI. And in black box AI, even though the algorithm was able to have a predictive interface and provide with some prediction result, the user often left wondering, can I trust this system? Why these predictions are so expensive or so cheap, or doesn't make sense? How can I find these errors? And that's just the user point of view, but we have also machine AI engineer also think about how do I improve the performance of the system. And when it comes to explanation, there is a difference between completeness and explainability. So there is a difference in the case where you can't just explain how the system making decision by explaining the model that behind it, right? You can be more detailed about how the model works, or you present a paper on that model. It does not mean that you are able to explain how the system making prediction. There's a separate strand. And finally, as all things in society, there is transparency versus bias and discrimination. And if the AI is a black box with no transparency, they also chance for it to make bias or discriminative decision if that exists in the training data. So, why do we care about explainabilities? And, it's mostly because of notion of trust. So let me show you an example here. There is an image of a dog, a husky, that was here get misclassified as the wolf. And you say, okay, fine, this image is gonna be hard for the model to understand. Husky look like dogs, and you might have some empathize towards this message. But what if you find out that the image patch or the image location where the model was using the most to make this prediction, you might have a different point of view. So the explanation for why this get classified as the wolf, and you see these are the image paths where the algorithm used the most to make this prediction, and you realize it wasn't looking at the dog at all. It was looking at the patch of snows around the dog, and the explanation for this, it could be most wolf would live in the snowy habitat, and that's why it kind of learned from from the training data. So by having this explanation, now you understand what happened to the model, and perhaps you can even figure out a way to improve it. Because obviously this model is not very good because it was using the wrong information to predict, even though it was correct in some case of the unforeseen data. But through human interactivity, we can improve machine learning system. Sometimes you need to verify the model, because what if your mission is critical and any wrong decision could be the difference between life and death? For example, self-driving cars or medical diagnostic tools. You could learn new intuition. For example, if AlphaZero is so good at playing Go, you want to know why AlphaZero must such a move in game of Go. And it also means that you can gain more insight in science. For example, figure out what gene linked to cancers and so on. And finally, we also need to address the inherent bias in machine learning system. You may heard on the face recognition model or some learn approval automated process as well. So the goal here is to have a explainable AI, having system where when the model have a prediction output is also come with an explanation. In this case, for housing, it also say the reason why the price for this range is because those reason, and so make the user understand why the AI was predict that value, and where succeed, or knowing explanations is also when to trust the system more. So the goal that we all want is design a trustworthy, reliable, and explainable AI without sacrificing the performance. So there are three ways for you to design explainability into the training process of the model. Number one is pre-training explainability. This is when you try to understand and describe the data set before training. In training explainability is when you develop inherent explainable model. And post-training explainability is when you already receive a trained model. Now you're trying to extract some explanation from that. So we're going to visit these three ways to design explainability. Number one, free training explainability. So we're going to look into the data rather than the model in this case. So you can use explanatory data analysis and visualizations. I know you have a lot of skills on this, but sometimes this rely merely on statistical analysis might not be good enough. And an example I show you here is these are different graphs plotting the data. And these data set, even though the shape, after you visualize it, look very different, they actually have the same means and standard deviation. So this is demonstrate the importance of visualization during the explanatory process of the data analysis. And you can use, a tool exists to help you visualize the data, such as parallel coordinate plots. You can use PCA to compress the data, or Tisney to visualize data in multidimensional, highly dimensional data. You can use dataset summarization, this technique, trying to seek the minimum subset of the representative example in the dataset called prototype that provide a condensed view of the dataset. So the image below is you see these are the prototype of the MNIST dataset, and you can kind of look only at these images and you kind of have a good understanding of what this dataset is about. However, prototype usually not adequate. It was good, but not adequate. Sometimes you need criticism as well. And a criticism is a often rare data points that are not well described by the set of prototype. So these are the example from the MNIST dataset. These are rare data points in there. So it give you another insight of how this dataset is. Okay, so that's mostly dealing with the features and the data points and not too much with the model. Next, we're going to look at the in-training explainability, where you see we're going to develop some inherently explainable model, right? So the number one model that you can kind of go to is the decision trees. In this case, we have a decision trees here where you can see how the diagnostic process, and again, this is a toy example, right? Is actually not just the only thing the doctor used to predict cancer, but you can see you can have some decisions and then derive more decision from the same decision trees here. So if you have developed model that based on this decision tree, your model is inheriting can be explained. Each of these features was explained why the decision were made. So if you adopt model from Pacific family, like the generalized linear model, decision trees, tree-based ensample model, or the generalized additive model, these are good model. But if you're looking at very large and complex data set, these model typically not perform as well as others nonlinear and neural network models. So, explainability shouldn't be sacrificed by the lower performance, right? So how we have the best of both worlds here? One thing we can try, we have some sort of hybrid architectures, and in this example, we're going to use the neural network, but we also look into the representation, different layers of representation in this neural network. And what we're going to do is we're going to develop a what called deep KNN approach, or keep a deep K nearest neighbor approach to use K nearest neighbors to inference from the hidden representation of this training data set. Right. So what we're going to do is that we're going to try to explain the outcome of each layer by its nearest neighbor samples, right? So for example, you want to explain why this example predicts certain, like panda here, then you would map this example to different hidden representation, and for each of those representation, you find the nearest neighbors. So you can explain this is the panda because throughout different representation is also have a lot of closest neighbor also claim label at panda, right? So that's what called conformity. And so if you go through here, panda, your nearest neighbor basically come from the same class, thus explain why the model make a prediction this is a panda. And this show to be effective when you have adversarial example that we talk about is the limitation of machine learning. So if you have some adversarial panda right here, what you can see is you want to do the same thing with the deep KNN mapping. You realize that there is many non-conformability among the data sets. So, for example, here, this panda now have non-conformal with the school bus and not its label at panda. So you can detect these sort of adversarial example using this deep KNN. Now, the only downside of this design is that you have to store all of the hidden representation of the entire training set. Which could be a daunting task, very memory constrained sometimes. So the most popular approach that people really worked on these days is called post-training explainabilities. And the one straightforward approach that you can think of is what called permutation feature important. And this is part of the model agnostic explanation. What it means is that you're going to treat a model as a black box and will not inspect any internal parameter of the model, but you're going to look at extracting some explanation on the model prediction. Right? So that's why I call model agnostic. So this method work with any trained model with n feature, and you need a validation data set. So what you do is first, you're going to compute the baseline prediction score on the validation data set. Typically, this is you already done anyway. So for each feature here, what you're going to do, number one, you're going to modify this validation data set by shuffling the value of that feature. Remember, we keep all the other features the same, only shuffle the value of one features. And then you compute the prediction score of the model on this modified data set. And certainly because you shuffle the features, the performance is going to be reduced a little bit. And that's exactly what you're going to compute. You compute the degree in model accuracy. And then you do that for all the features, right? And then what you're going to do is now you have all this. For each feature, you have a decrease from the baseline, so you can rank all the feature across your all the features according to the reductions of their score compared to the baseline. Thus, the higher the reduction, the more important the features are. So that is sort of work mostly with the tabular data, right? Tabular numerical data. But what if you have others? Type of data, images, and audio, and text, and so on, right? So there is research group by Marco Ribeiro in 2016 come up with a method called LIME, or local interpretable model agnostic explanation. And the way it works is it works well for images. So the way it works is to explain the prediction of any classifier by learning the interpretable model locally around the prediction. So the way it works is to treat the model as a black box. What it does is just you take in any test image, and the model will be able to produce some sort of score or probability for this image belong to a certain class. And what it's gonna do now is that it will be able to try to perturb this input image, maybe break into multiple parts, right? So this image can be break into multiple chunks. And what it does is it make a perturbed instant of this image by blocking out certain chunks and while display in the other. So you can see here it displayed by all the gray pixels, and also think about it like block it out from in an input signal and why allow others pixel to get through. And with this technique, it can generate lots and lots of perturbed instances. And for each of these instances, you can run through that black box model and produce a score. Right, so you have this sort of your own data set of this training example and produce a distribution of score. And you can then learn a local linear regressions on this data set, so that you can understand how it behaves in a small local environment. And from there, you can learn which region or which pixel possibly correspond to the score of the model on the original image. Thus, you learn the region that explain why it's making that decision. So using this technique, you able to learn which region on the test image that's responsible for the prediction. Right? So let's get back to our Husky predictions, and the Husky was actually on this line method. So you can see here you predict a wolf and actually a husky, and the result is based on the snow. You can see on this side it would correctly predict a wolf by just looking at the snow patches and slightly some patches on the wolf fur. But when it comes to husky, then it start looking at like the dog features and so on. So using this line technique, it kind of gain some intuition about how the model actually making these predictions, right? Okay, and Rise, another technique, take on Lime and improve it for randomized input sampling. So the way it works is for the test input image, you're gonna generate random mass. So you're gonna element Y multiply an input image with random mass. So at the result, you have some mass image. So these are not just patch. These are still patch, but these are all more randomized, right? So you have a bunch of these images, and you feed that again into black box, and you get the score. And then what you do is you take in this score, and it's become a weighted sum to the mass. And if you do a weighted sum of these score on the mass, what you get is a heat map at a linear combination of the mass, where the weight comes from the score of the target class, corresponding to the mass input. And the nice thing about this is that you can apply it on maybe a image captioning application. And what happened is, given an image, and you had to pair this with a attention model. But basically, what it can do is it can produce heat maps. Depends on what words are generate at the time, what caption is generated at the time. So, for example, here, if you generate a horse, then you can generate a heat map to explain why it generate such a word, right? So, a horse here, you generate a carriage here. This is what it's using, and you can input any sort of words into the model, and it would try and explain why it do something. So, for example, here you have a somewhat random input at white, and it would generate the image that explain why if this model would generate the word white, right? So it is like white horse and white building and whatnot. So that was pretty cool. Come to generative model. There is worked on GAN dissections. And the way it works is that we try to identify some interpretable unit within the generative network. And the feature maps are highly correlated to a region of the object classes and generated by the network. So for example, if I was using the generator George here to generate some images. I can run some segmentation on these images to maybe extract like region of trees. And from there, what I can do, I can find some agreement between the segmentation and a constructed image from some feature map. Like you upsample this feature map, you might end up with some thresholding image that represent close to the segmentation, right? So if these two are in agreement, you then identify this feature map may be responsible for generating all the trees or the leaf in the image. So that's kind of cool. If you this example show you all these generated image of churches, and you were able to identify the GAN with a unit in the generator that match the tree to generate the tree. From there, you can kind of explain why this network generate tree, and you can manipulate it. You can remove this unit to generate less tree or no tree, or you can activate this unit even more to add more tree into generated image. So that was pretty cool. Now I'm going to show you the last example on differentiable physics engine for deep reinforcement learning. And you've seen this in the reinforcement learning lecture where the deep reinforcement algorithm was able to outperform human tester. But what the problem it takes such a long time and taking a lot of training data in order to start getting really good performance. So the reason you have this is 10 to the 7 here, so up here about 10 to the 8 steps, which is take a lot of training data. And the reason for this is because the type of input is just based on raw pixel image. And so there is a group that argue that what if we have, and this pixel image, typically is not differentiable. So there's a group of research argue that if you have a physics engines and you were able to integrate this physics engine at a deep neural network model, you might be able to allow end-to-end trainings here. Because beside from this input, you might have some dynamic model to integrate into this end-to-end pipeline. And if your this physics engine be able to having differentiable functions, which you can perform backprop analytically, defined by a linear problem, you might be able to improve the performance of the network using a lot less training, right? So this way, the learning rate for this network improve a lot faster, doesn't take much time at all, and it have comparable performance to the deep reinforcement learning. Now the details of the papers, you certainly can go on to the reference here if you want to find out more about it. I know we go into a very high level, but you certainly can find out more if you're interested in these kind of things. All right, so in summary, user prefer explanation, and explanation generate trust. That's why explainable AI is become such a trendy in research these days. Explainable AI, or XAI, is very important to developing trustworthy and reliable AI system. And we talk about pre-training explainability, aim at understanding and describing the data features. In-training explainability to aim at develop more inherent explainable model, and post-training explainability to extract explanation from trained model. So all of the approach are interesting, and hopefully in the future we're gonna have much more promising work to hopefully develop a XAI best practice. So there's exciting few to come, and if you show in the Google trend, this explainable AI the past few years had training up, so there's more attention paid into it. Okay, this is all we have for this videos, and it's certainly a very exciting topic, and I would definitely encourage you to find out more on your. I'll see you in the next video.